Okay, you can ask a question at the end of the session, so please keep thinking. All right, so let's move on. Our last but not least speaker is Cecil Sun. She's a Master of Engineering student in Computer Science at Cornell Tech. Her research interest includes wearables, game design, and machine learning. And she's going to graduate with her master's degree this year and will be in the job market soon.
Thank you for the introduction. Hi everyone, I'm Ruza Sun, and you can call me Cecil. And today I'm really excited to introduce EchoNose, a non-contact nose interface that can sense mouse, breathing, and tongue gestures inside the oral cavity. So first of all, why is mouse gestures important? So this is because they open a new form of interaction. We can see them in VR systems to provide a new input layer, and they are also seen in accessibility technologies, for example, wheelchair control. However, tracking mouse gestures, especially tongue gestures, has been challenging. Previous work either requires instrumentation inside the mouth or heavy instrumentation outside the mouth. So this raises a question that, is there a way to track tongue gestures with a lighter and less intrusive interface? Here we present our prototype EchoNose. We attach a pair of microphone and speaker to an off-the-shelf glass frame, and they cost less than $10 and have a low power consumption. The microphone and the speaker is attached under the participant's nostrils without contacting their skin. So our system is non-contact and non-intrusive. So how does our system work? The speaker placed under the participant's nostrils will emit signals that travel through the nasal and oral cavity. These signals are then reflected back and get received by the microphone. Different gestures will cause different multipass echoes, which are then recognized and via an analysis of the echo profiles. Let's take a deeper look. So we use FMCW-based acoustic sensing, and the speaker will emit signals that are inaudible to most humans. And we get an echo profile that visualizes the activities near the microphone. In terms of deep learning, we use a customized model to classify our gestures. We designed our gesture set with 16 gestures. The first four of them are tongue gestures: tap, back swipe, left cheek, and right cheek. They are for simulating directional controls, for example, scrolling and swiping. To demonstrate the capability of EchoNose providing a more diverse interface, we included silent speech and breathing patterns as well. For our silent speech, we included 8 words, where the first 6 words are for menu-based applications, and the last 2 words are for simulating possible gaming actions. In terms of breathing patterns, we have gale, gust, wop, and calm, which are inspired by previous work. In our user study, we recruited 10 participants, and each of them remounted our device 15 times. This results in an over 1,000 gestures per participant, and overall, we get a promising result of 93.7% on the 16 gestures previously combined. We also took a deeper look into each subgroup of the gestures. While the silent speech and the breathing patterns has a great performance, it is slightly harder to track the tongue gestures. This is expected because the tongue gestures are completely inside the oral cavity, and the echoes need to travel a longer and winding path. Next, we'd like to discuss some of the limitations and future work of EchoNose. So although EchoNose is a non-contact and non-intrusive interface, we acknowledge that our current form factor might not be socially present or acceptable for many users. To mitigate this problem, we can integrate EchoNose with larger size systems that occlude the nose, for example, VR headsets, face masks, and Dyson headphones. This can be an important direction for the future work. Thank you, and please refer to our paper for more details.
All right, any quick question? Okay, maybe we can keep this. Oh, please go ahead.
I'm curious whether there's a situation when people just speak that they accidentally be recognized as one of the gestures.
So basically, our gestures are like based on silent speech, which is using the echo profiles that emits signals that are mostly inaudible to most humans, so this won't be confused with the voice speech because they are in different channels. Okay. This is an interesting question, and which might be able to we might be able to look into in the future work. Thank you for the comments.
All right. Thank you for great presentation.